Welcome back. We were looking at the process of returns to state j, right. So, let us say the Markov chain starts at state j, right, at time 0, and then it visits a bunch of states and then returns to state j at some point and so forth, right. We looked at fjj infinity, which is the probability of eventually returning to j given that we start at j, right. So, if this fjj is equal to 1, then we said j is recurrent, and it is less than 1, so j is transient. All right. Then, so in the case when if j is recurrent, then this tjj is less than infinity with probability 1, right. And then we said that if you look at these times of subsequent returns to j, tjj1, tjj2 and so on, tjj1, tjj2 are IID. Okay, this is from the strong Markov property. We said that if you start at j and first time you return to j, the subsequent evaluation after tjj1 also satisfies the same transition probabilities, and this is the strong Markov property that we studied in the last module, right. So, using this we can argue that the times at which state j occurs, successive returns to state j occurs for a recurrent state j constitute a renewal process. Okay. So, we can argue that successive returns to state j constitute a renewal process. Okay. Using this, we can straight away get some results that we know from renewal theory, all right. So, let us do that. Let me say njjt is the number of times j is visited in so up to time t included. Okay. And we can already state this theorem starting at j, right. So, let me say starting at state j. The following are equivalent. J is a recurrent state. Number 2, limit t tending to infinity n j j of t is infinity with probability 1. Limit t tending to infinity expected n j j of t is equal to infinity. Number 4, limit t tending to infinity sum over n is equal to 1 to t p jjn is equal to infinity. Okay, so this theorem says that the following statements are equivalent, that is j is a recurrent state if and only if the number of returns to state j until time t goes to infinity as t goes to infinity with probability 1, and the expected number of visits to state j until time t also goes to infinity, and finally the sum of these probabilities goes to infinity. We are saying that all these 4 statements are equivalent, all right. Any one of this implies the other, vice versa, all right. Proof, right. So, this is fairly easy. Suppose at least the first 3 are fairly easy. Suppose state j is transient. Okay. This implies that this by definition is saying that fjj infinity is less than 1, all right. So, the probability of starting at j and eventually returning to j is strictly less than 1. Okay. This implies that the total number of visits to j starting at j is a geometric random variable with mean fjj over 1 minus fjj, right. This is because you have a positive probability, namely of 1 minus fjj of never coming back to j, all right. So, if you start at j and come back to j, there is a probability of doing that is fjj infinity, and that is strictly less than 1, and you can, the number of times this will happen is simply the number of times this this, it is as though you are tossing this coin with probability fjj infinity. So, if it fails, with which happens with 1 minus fjj infinity, probably 1 minus fjj infinity, then you will never return to j. Okay. So, the number of times you will return to j can be shown to be a geometric random variable, all right, with finite mean, right. So, which means that the number of returns to j starting at j and the expected number of returns to j starting at j are both finite, right. This guy is a finite number. Right. So, if j is transient, the eventual number of returns to j as well as the expected number of eventual returns to j are finite, all right. So, this implies that for a recurrent state, so this establishes that if the number of returns to state j starting at j and that expected number of returns is infinite, then the state j must be recurrent, right. Because if it is transient, we know that the expected number of returns to state j is finite, right, and the number of returns is also finite with probability 1. Therefore, if this number is infinite, then the number of returns to j must be then state j must be recurrent, all right. So, that establishes the implications of 3 and 4 the 2 and 3 implying that state j is recurrent is clear. If state j is recurrent, of course, we know that njjt is a renewal process, and therefore, we know that limit t tending to infinity njjt is infinite with probability 1, and expected njjt is also goes to infinity as t tends to infinity. Okay. So, we can easily argue that the first 3 statements are equivalent, right. So, this implies or if limit t tending to infinity expected njjt is equal to infinity, then state j is recurrent. Conversely, if state j is recurrent, njjt is a renewal process. So, that implies 2 and 3. All right. So, we have proven the equivalence between 2, 3 and 1. Finally, we have expected. So, this is for proving 4. Expected njjt is the expected sum over indicators, right. If I can put n equals 1 to t, indicator x n equals j given x naught equals j, all right. Now, this is a finite sum, so I can take this inside, that is equal to why. So, why is this relation valid? So, njjt simply counts the total number of times you have visited state j until time t, right. So, you are counting simply the indicators x n is equal to j given x naught equal to j and summing from n equals 1 to t, right. You are looking at, you are summing all the indicators from n equals 1 to t, whether x n equals j, right. So, this becomes, of course, I can take the indicator inside because this is all a finite sum. So, I can take this becomes probability x n equals j given x naught equals j is equal to p j j n, all right. This is true for all t. Now, therefore, taking limit the equivalence of 4 follows. Okay. So, if I send t taking limit t tending to infinity, I can get the equivalence of the fourth statement with the other 3. Okay. So, we have so far looked at starting at j and returning to j. Now, what if I start at some state I, okay, then I look at subsequent returns to j, okay, this may be k, l, whatever, all right. So, if I start at I and look at the instances when I return to j, what happens is that, so this will be a, let us say, some atypical time t I j, right, and then subsequently again by strong Markov property you can argue that these will all be like your usual recurrence times of the state j starting at j, all right. So, if I say nij, let us say if I define this nij of t is equal to total number of total number of visits to j starting at I, all right. If j is recurrent, and if I and j belong to the same class, then nij of t is a delayed renewal process. Okay. So, the only difference now is that I am starting at some other state I, which is in the same class as j. Okay. So, if I and j are not in the same class, you may never go from I to j, right. So, you go from I to j in some finite time t I j, and then you look at subsequent returns to j, right. So, this t I j alone is atypical, then you have typical recurrence times of state j to state j, right. This n I j of t, which counts the number of times you visit j until time t, so number of visits to j until time t, starting at I. Okay. This n I j of t turns out to be a delayed renewal process. Okay. So, what we know about renewal processes and delayed renewal processes, including strong law, elementary renewal theorem, renewal reward theorem for both renewal processes and delayed renewal processes, can be used to derive useful results about Markov chains. Okay. Now, we have seen that Tjj less than infinity with probability 1, the same as saying j is recurrent. Okay. So, Tjj, the time between successive returns to state j, if it is finite with probability 1, then you say that j is recurrent, right. Now, what about the expectation of Tjj, right. So, we know that Tjj, so then this returns to j will be a renewal process, but what about the expected renewal time, right. Question: is it finite? Is okay. So, whenever you have a renewal process, let us say IID X renewal process, you can always apply these renewal theorems now, but usually you have 1 over x bar coming in the denominator and all that, right, 1 over expected x. So, we have to look at what is this expected value of this renewal interval, right. Is it finite? Okay, see, generally this expected Tjj does not have to be finite, okay, even if Tjj is finite with probability 1, right. So, this we know, right, this is basic probability. Even if Tjj is finite with probability 1, expected Tjj may or may not be finite. So, it is possible to have a random variable Tjj which is finite with probability 1 by definition, but its expectation may be infinity. Okay. So, this further subdivides these recurrent states into two types. Okay. Definition: suppose state j is recurrent, so suppose state j is recurrent. Definition: j is said to be positive recurrent if expected Tjj is finite. J is said to be null recurrent if expected Tjj equals infinity. Okay. So, this further divides states in a countable state DTMC. So, Tjj is finite with probability 1, state j is recurrent. If furthermore, if Tjj has finite expectation, then the state j is said to be positive recurrent. If expected Tjj is infinity, then we say that state j is null recurrent. So, you could have a state. So, you have so if you have a state j, it could either be transient or recurrent, right. So, if this is Tjj is less than infinity with probability 1, you have a recurrent. If Tjj is equal to infinity with probability greater than 0, then you have a transient state. Recurrent states are further subdivided into positive recurrent and null recurrent. Okay. Positive recurrent is if expected Tjj is finite, and a recurrent state is said to be null recurrent if expected Tjj is infinity. Okay. So, that is the picture. Now, as it happens in finite state Markov chains, you never have null recurrence, you have only recurrence and transients. This null recurrence is something that occurs only in these countably infinite state Markov chains. Okay. This you can show. So, now let us start applying renewal theory and delay renewal theory to these return times, all right. So, these processes. Suppose J is recurrent, then the counting process njjt, remember njjt is the total number of returns to j starting at j until time t. This satisfies these two things: limit t tending to infinity njjt over t is equal to 1 over expected Tjj with probability 1, and 2 limit t tending to infinity expected njjt, the expected number of returns to state j starting at j until time t is equal to the same thing, okay. So, this is nothing but strong law. So, njjt is a renewal process. So, it must satisfy the strong law for renewal process, and this is nothing but the elementary renewal theorem, which you are familiar with, all right. And this is true for both positive recurrent, positive and null recurrent state j. Okay. So, remember that this strong law for renewal process and elementary renewal theorem are valid even if expected x is infinite. So, we do not require that. In this case, we do not require that state j be positive recurrent. It is okay if it is positive recurrent, it is okay if it is null recurrent, all right. And this does not require a separate proof because we have already studied strong law for renewal process and elementary renewal theorem. Similarly, if you look at the Nij process, right, suppose state j is recurrent and I is in the same class as j, then the counting process Nijt satisfies limit t tending to infinity Nij of t over t is equal to 1 over expected Tjj with probability 1 and limit t tending to infinity expected Nijt over t is equal to 1 over expected Tjj. Okay. Remember this, I am looking at Nijt, but here I have expected Tjj, not Tij. Okay. So, that is because if you remember the picture, you are starting at I, right, which is in the same class as j, but j is the recurrent state. Okay. And for this I am looking at the number of returns, number of visits to j until time t starting at state I, right. So, what really matters is this expected Tjj. Okay. This Tij does not matter, if you remember, right, from renewal theory we know that this first atypical time Tij does not matter. So, limit t tending to infinity Nijt by t and its expectation are both equal to 1 over expected Tjj. Okay. This is basically strong law for delayed renewal process and elementary renewal theorem for delayed renewal process. So, these results are quite useful. Okay. Now, let us state an important theorem that says that all states in the same class are of the same type, i.e., either all positive recurrent or all null recurrent or all transient. Proof. See, remember that we have already proven that the states in the same class are all either recurrent or all transient, that we have already proven, right. So, now we have to, we are just defining this, right. If a states in the same class are all either all positive recurrent or all null recurrent or all transient, right. So, we just have to prove the positive recurrent and null recurrent part, right. So, recall we already proved this theorem 6.2.1 in Gallagher says all states in a class are either recurrent or all transient. Suppose J is positive recurrent and I is in the same class as J. Okay. So, now I am looking at a class. Okay, so, J I know is positive recurrent, I am looking at some other state I in the class, right. I want to prove that I is also positive recurrent. I know that I is recurrent, right, but I do not know whether it is positive recurrent, that is what I have to prove. consider the renewal process njjt and associate reward of 1 let me say ri of t equals 1 whenever the state is I. Okay. So, I am associating a reward process. So, I have a renewal process njjt, I know that j is positive recurrent, okay, and I am associating a reward process ri of t which is equal to 1 whenever the chain is in state I, alright. Now, I can apply the renewal reward theorem, alright, which says that limit t tending to infinity 1 over t integral 0 to t ri of tau d tau is equal to expected ri over expected tjj, alright. Now, this is nice, right? This is from what? This is from renewal reward theorem, right? Now, why is this relationship nice? Now, we know that expected tjj is finite, alright. So, we have expected tjj is finite because j is positive recurrent and expected ri should be strictly greater than 0. Why? Because I and j communicates, they are the same class, right. So, whenever I am starting at j, there is at least a positive probability that I will visit I, right. So, the expected reward, I get a reward of 1 whenever I visit I, right. So, the expected reward cannot be 0, it has to be strictly positive because I and j are the same class, alright. Therefore, the RHS is strictly positive, right. So, this is of course almost surely. So, what does this mean? Limit t tending to infinity 1 over t integral 0 to t ri of tau d tau is something strictly positive divided by something strictly finite, right. So, this will be strictly positive, right, almost surely. Now, what is this, right? This is the, so remember you accumulate a reward of 1 whenever you are in state I, right. So, this is the number of times you visit, so this is the expected number of visits to state I starting at j, right. This is nothing but it is not the expected. So, this is the time average number of visits to I starting at j, right. What is the time average number of visits to I starting at j, right? It is nothing but this is equal to 1 over expected t I, right. So, if you start at start at j and you are just counting the number of visits to I, right, you are simply counting. So, this is just the n j I of t, right, divided by t. So, that is what this guy is equal to that guy, right, and the limit t tending to infinity of this by the previous delayed renewal theorem, right, by the delayed renewal theorem that we had in this here, right, by this result here is equal to expected 1 over expected TII, right. So, that is excellent. So, this implies 1 over expected TII is strictly positive, implies expected TII is less than infinity, right, implies state I is positive recurrent. Okay. So, if I start with a positive recurrent state J, I have shown that any other state I in the same class must be positive recurrent, right. So, even if there is one positive recurrent state in the class, then the entire class is positive recurrent, right. So, this proves what I want, right. So, I am done, this proof is done. But this equation, I want to go back to this equation, which is I want to rewrite this maybe in words, right. So, let me call this star. The star will be useful later. Okay. So, what does it say? It says 1 over expected TII, which is the left hand side, equals expected number of visits to I between successive returns to J. Returns to J divided by expected TJJ, all right. And this relationship is valid as long as J is recurrent and I is any other state in the class. Okay, that is all that I need. I do not even need positive recurrence for this to be true, right. This is almost surely, right. Sorry, so these are just numbers, there is no almost surely here. So, the left side of that integral is equal to 1 over expected TI bar by strong law, okay, almost surely, and the right is equal to expected number of visits. So, this is nothing but expected RIT, right. So, you are looking at this process starting at J, right, and you accumulate a reward of, whenever you are in state I, you accumulate a reward of 1, right. So, expected RIT is the expected number of visits to I between successive visits to state J, right, divided by expected TJJ. Okay. So, this is a very useful relationship. Okay. We will probably come back to this, or you can rearrange and write it as expected number of visits to I between successive returns to J is equal to expected TJJ by expected TII. Okay, this will be useful when we do steady state probabilities and all that. Okay, okay, this module can be stopped here.